Hello, I'm Huiling and I'm doing my PhD in the Aeronautics Department, and I'm also a fellow of the Software Sustainability Institute. Today, I'm going to be talking about atomic commits, what they are, and why it's worth taking the time and effort to make atomic commits. Last time, we looked at how to write good commit messages, such that they can be used for debugging and understanding the rationale behind the implementation of the code, as well as what makes a bad commit message. Introduced was a skeleton for writing useful commit messages. Each commit should start with a concise line summarizing the commit. If additional context is required, then an empty line should be left between the first line and the subsequent paragraphs containing the details. Having good commit messages is only the first step to solving the problem. It's the linchpin for navigating and finding specific details in the Git history. Without good messages, the log will be a mess of gobbledygook and will render the next step ineffectual. The second step involves crafting atomic commits, which are commits that only contain one logical change. Thus, the contents of the commit message would be specific and relate only to that single change. This has the side effect of making it easier to write the first line which summarizes the commit. A general rule of thumb is that if you find yourself using AND as a way to list things that have changed or been fixed, then it's highly likely you've got too much in a commit. By attempting to write a useful commit message and knowing how to describe the change, it becomes easier to identify whether or not your commit will be atomic. You might be thinking that it's fairly obvious as to why good commit messages are important, but why would atomic commits matter? Let's consider how I spend my time. When I first started out, I thought I'd be spending most of my time writing code. I'd be churning out hundreds of lines of code each week and getting so much done. Over time, I realized I spent very little time actually writing code. I'd usually start by spending a lot of time thinking about what is the problem and how I could go about solving it. Once I've scoped out the problem and knew what I had in mind, then I'd move on to spending a fair amount of time reading the code base I was working on and the documentation of the package I was using, or even reading other people's code to figure out how to implement a given feature. It was only once I had an idea of what is possible that I'd start experimenting with small bits of code and planning how to get this to fit into my whole code base. When I encounter issues and I'm stuck debugging, I often spend most of that time reading more code and more documentation to figure out what's going on and how it all works. Since writing code takes up the least amount of time, it meant I had to find ways to make all the other aspects easier and smoother. Atomic commits helps to achieve that. There are 5 reasons to why I believe atomic commits are important. The first is that it helps make problem solving easier. As each commit should only contain one logical change, it forces you to break down the problem into smaller, manageable chunks. My instinct when faced with a problem is to throw myself headlong into it without stopping to think about what the steps involved are. Breaking it up into smaller pieces from the outset not only minimizes the cognitive load of larger tasks, but also makes it easier to track and document your progress. Let's consider this feature, plotting a best fit line through experimental data. If you're familiar with writing code and automating such tasks, this would sound very simple without much to it. Let's first assume that the data is stored in a CSV file format. The first step to the problem would be to load it. Then I would want to compute a linear fit through the data and finally creating a plot. If, like me, you tend to dive straight into the problem, then there might be some finer points that you've missed. When loading your data, there could be additional pre- and post-processing steps or computing additional variables from the raw data. Even with the linear fit, there could be an additional step of assessing the quality of the fit. And finally, creating the plot involves both plotting the raw data and the fit. This practice encourages modular thinking and improves implementation by breaking components into small, single-purpose functions. What counts as the smallest part and whether that's enough for its own commit comes down to judgment, team conventions, and the kind of history that you find most useful. The next benefit is that it helps promote a cleaner, more readable Git history. Consider this graph of Git commits. From the identifier, which I've hijacked to put a very concise message, we can see that they are not atomic commits, as the first commit implements 2 features and the last commit fixes a bug and has a new feature. A graph with atomic commits will look like this. Here you can see that the first and last commits have been split into 2 separate commits. As each commit contains a smaller chunk with a targeted meaningful message, it's easier to see what each commit does and why it was made. These make it more readable and easier to navigate. Moreover, with smaller chunks of work, you'll finish them sooner and end up committing earlier. This means that you're able to keep saving your work as you go and get this huge sense of accomplishment each time you commit and won't risk losing any of your progress. This demo is to show how having multiple changes in a commit makes it hard to pick one out from the other. I'll be scrolling through some code and please don't attempt to read it. From this commit message, we can see that there are 2 changes associated with this commit. The first change is related to a logic bug, and the second is related to how the closest pressure level is computed. Now, I'm going to show what the changes are. From the first few lines, we can see that those changes are related to computing the closest pressure level. The next set of changes are a blend of logic fixes as well as this closest pressure level change. The remaining changes are all related to the closest pressure level. If I decide now that I want to split these unrelated changes up into smaller components, it'll be a real pain. However, if I had made small commits to begin with, I can combine them as I please. The third benefit is that it's easier to revert and amend any commits. Consider the case where the changes in fix for bug in A are problematic, so the goal is to undo the changes associated with them. In the non-atomic commit case, this is messy because it's tied with another set of changes. The only solution that I have found for this is just to manually find the changes and delete them. However, in the atomic commit case, these changes can be easily removed. This is a demo to show how a commit can be reverted and how important it is to only have one change. From the Git log, the commit that I want to revert is the most recent one, with the hash of 5b2cc7d. Running git diff between the latest commit and the current state of my repository shows the text that has been added. Now, I'm going to use the commit hash from the log to revert this commit. Reverting the commit prompts for a message to be written. As I don't need to change the default message, I'll leave it as it is. Running git log again shows that I have a new commit that reverts the previous commit. Running git diff between the latest commit and the current state of my repository shows that an inverse change has taken place, with the text in red and minus to indicate this text was removed. Running git diff between the second last commit and this commit shows that there are no changes because this has already been reverted. The fourth benefit of atomic commits is that it makes debugging and testing easier. In the previous talk, we saw how good commit messages can help with understanding your code base and for debugging. However, there is a limit to it. This method will only allow you to understand how the code works. From there, reason out the cause of the issue. It will not help with pinpointing when exactly the regression occurred. If you now combine atomic commits, good commit messages, and tests, your code now becomes bisectable. Thus, it's now possible to pinpoint when the bug was introduced. So, what does it mean for your code to be Git bisectable? Imagine this case where you know that at commit good, your code works, and at commit bad, the bug is present. This means that the bug was introduced in one of these commits. To locate the bug, we're going to use git bisect. The process starts by invoking git bisect start, then by telling the git bisection algorithm the commit where the code works. Since good doesn't have a commit hash here, I'm going to use the hexwork decaf. Then we're going to tell git where the code doesn't work, which is at the start of main. Git then checks out to the middle commit. We'll now run tests to find out whether or not our code works at this commit. If it does, we'll run the command git bisect good, and if it doesn't, we'll run git bisect bad. Now let's assume that our code worked. Git will now check out to the commit that's between the current commit and the broken commit. Repeating the process again will eventually bring us to the commit where the bug was introduced. This can work with non-atomic commits. However, it will involve digging into the commit itself to find which component of it caused the issue. With atomic commits, it brings you exactly to the changes that caused the bug. The most important caveat to this method is to remember that tests need to test the correct behavior of your code. It's easy to write tests that appear to test the functionality of the code, but in fact just check that certain bugs are in place. After all, tests simply check that the execution of your code matches what you have defined in the test. Git bisect is a fantastic tool for finding where a regression took place. Adding continuous integration, or CI, into the mix can prevent regressions from being introduced into your main branch in the first place. Continuous integration is the practice of integrating the source code frequently and ensuring that the integrated code base is in a workable state. This is an example of a repository on the college's GitHub. This badge here in the README shows the status of the CI workflow for the master branch of the repo. How this works is that whenever a change is to be added to the main branch, this GitHub action called CI is run. Here you can see that the action was triggered by a pull request related to updating the dependencies, and the status of the action is failure. 2 jobs called build have failed. On the right is a screenshot of where this action had failed. You can see that it failed at the test with PyTest step with 2 failed tests. These failing tests have caused the action to fail, thereby preventing these changes from being added to the main branch. Remember, tests and such safeguards are only as good as you make them. It's possible to have tests which don't do a good job at testing the functionality, tests which aren't sufficiently comprehensive, or tests which will always pass. Or an alternative solution is just simply getting rid of the failing tests. The main reason I take time to write tests is that they let me build on my work with confidence, and they give me the assurance to keep moving forward without feeling like everything is a house of cards. Plus, the best way to destroy time off is for live code to break in production. The final benefit of atomic commits is that it facilitates collaboration. One of the most painful parts of collaboration is dealing with merge conflicts. Merge conflicts occur when 2 people work on the same lines of code, such combining the changes results in conflicts. With smaller chunks of changes, the conflicts become easier to manage, as 3 to 5 lines are always easier than dealing with 20. We have seen the 5 reasons as to why atomic commits are useful. The best technique to ensuring your commits are atomic is by working with one aspect at a time. However, in research, this is often not so clear-cut. So, how do we take a set of changes and break it up into smaller bits so that only parts that we want are committed and the others are not? When working, I'm often not disciplined enough to ensure that I work on only one thing at a time. To make my commits atomic, I often have to look over my changes and break them up into the component parts. In this demo, I'm going to show how to use git add-p to achieve this, and there will be a lot of code flashing by. Please do not attempt to read it and understand why it falls into a given category, as this demo is just to show how this can be achieved. From the diff, you can see that there are a lot of changes, which are not strictly related. I want to commit the changes that are related to documentation. To split the changes up, I'm going to use git add patch. This breaks the changes up into blocks so that you can select which bits to add. As I want to add this change that is being shown, I'll pass y to indicate yes. For the next set of changes, I don't want to add them, so I'll pass n, no. In this set of changes, I know that I want to add some of them, but not all of them. So I'm going to tell Git to split up the changes. Now I'll pass yes and no accordingly based on what changes I want to add versus reject. The exact same functionality can be achieved with your IDE. They often have nice interfaces to do this operation. Running git diff staged shows that it only has the changes that were added. Now, I want to make a semantic commit specifying that it's related to a documentation change and explain what the changes are. Since it's a fairly straightforward change, I've not added additional details explaining it. Running git status shows that the changes are still present and git log shows our newly created commit. To summarize, making atomic commits brings clarity, control, and consistency to your workflow. Many of us have experienced that familiar moment returning to work after the weekend and wondering, what was I working on Friday? Atomic commits helps to reduce that uncertainty. By committing small, focused changes as you progress, you create a clear, traceable record of your work. This allows you to quickly identify where you left off and resume seamlessly. Additionally, atomic commits simplify maintenance. When each commit represents a single, well-defined change, it becomes far easier to review, revert, or remove unnecessary commits. In contrast, large or mixed commits makes it difficult to isolate specific changes and can lead to data loss if progress isn't properly saved. In essence, atomic commits are not just a version control best practice, they are a key habit for improving productivity, traceability, and the overall code quality. This is the fourth talk in the series. The next talk is about how branches are beneficial even without collaborating with anyone, why they are useful for ensuring that you always have a working version of your code, experimenting with new features, and the organizational benefits of it. Thank you, and I hope you enjoyed my presentation.